Welcome, everybody. So this is module 2 of performance, portability, and productivity. So let me, hopefully everyone's able to see the screen. So just the schedule of this learning series. So last month we did the first part, which was introduction to performance, portability, and productivity for HPC. And today's session is going to be about optimization best practices using SYCL. And then next month, we will follow that up with optimization for performance portability across CPUs and GPUs. And a week later, we have this a fourth part where it's mostly something that you guys can come up with questions. We will have some Intel experts or more like a working session. Right? So just to recap what we did last month. So the video for last month's session is available if people haven't attended that. So mainly we took a look at performance, portability, and productivity. Why is it important? We identified an algorithm and implemented using math kernel library. And also we implemented the same algorithm using just basic SYCL programming, right? And we also did some analysis using Intel Advisor and vTune Profiler. And we did the performance analysis on 4 different accelerator hardware, 2 GPUs and then 2 Xeon processors. So we will quickly do a recap before I start the actual session. So this is what was last month. So on today, mainly we will look at how to use some SYCL features to tune the basic algorithm that we created last month. We will learn about ND-Range and then the impact of workgroup sizes. We will look at how to use private memory and then shared local memory to improve performance. And finally, we'll do some analysis using Intel Advisor Roofline and also Intel vTune Profiler. So that's today. So what's coming up next month? So we will do more optimization for mainly performance portability across the CPUs and GPUs. And we will understand the characteristics of different accelerator hardware that we are using, and also look at how to understand the impact of accelerator occupancy and also how it impacts the varying workgroup sizes. And we will do more optimizations. And finally, we will look at more advanced tuning using the oneAPI GPU optimization guide. Right, and finally, we have a 4th session, which is mainly going to be like a working session or a hackathon. So you guys can bring your own code and share and ask any optimization related questions. We will have a bunch of Intel experts and we will have some breakout rooms. So do let us know between now and March 16th if there's any specific topic you want us to cover in this last session, or you can share your code and then we can help you with any optimizations, right? So your feedback is very important. So we did receive some feedback and questions. So one thing that I wanted to highlight is somebody asked about, they wanted to know more explanation about the commands that is nicely wrapped in the script under the hood. So I will take about 5 to 10 minutes to do a review of the various scripts we are using in the hands-on session. So please do let us know questions like this. So we will definitely address it in the next session. So with that, let me switch over to the Dev Cloud, and we'll start with a quick recap. Okay, so before we start the session, so there have been some updates. So if you are logged into the Dev Cloud, you will probably see a bunch of these courses available. So what we are looking at today is DPC++ performance portability. So if you got this module last month, there are some updates that I did. So if you want to get an updated copy, so please do run this script here. So let me paste that in the chat window. So hopefully everyone is up and running with their Dev Cloud and then Jupyter Lab. So in the terminal window, just paste this command, and this should actually update to the latest. So you guys should actually see a bunch of different changes here. So once you've done that, so this folder will be updated. So if you're seeing any issues, you can also just delete this entire folder and then do this update script, which will copy over the new modules. So let me start with a quick recap what we did last month. So mainly last month we looked at two implementations of a basic matrix multiplication algorithm. So we looked at how to implement using the math kernel library and also how to implement using basic SYCL features, right? So we looked at the math kernel library. You can see that we have the kernel code here. So all we are doing is like just adding one library command, and this will do the job of matrix multiplication. And then we looked at the various roofline reports that it generated. So I have like reports from DG1 with various matrix sizes. You can see that we have a report for 1,000 by 1,000, 5,000 by 5,000, and 10,000 by 10,000. So same thing with VTune results. We have results from Gen 9 as well as DG1, and you can see that with varying matrix sizes, you have different performance numbers here. And we also looked at the basic implementation, which is just using the SYCL features. You can see that the kernel code is right here, and we just created accessors for the matrix input and the two input matrix and then the output matrix. And you can see that we have a read mode for the two input matrix, and then we have a output matrix, and then we do a simple matrix multiplication using a basic parallel for kernel. So this is what we looked at. And again, we have the reports available. And if you actually do the analysis and then capture numbers for various matrix sizes, you can see that overall, you can see that for the MKL version, using the library gives you a lot better performance compared to the basic implementation using SYCL, right? But if you do, you can see in one case, when you're using smaller matrix sizes, you do see that MKL, because of the overhead, is not giving better performance. But once you start increasing the size of the matrix, you can see that it is significantly better than the very basic implementation, right? So this was what we did last month. So today we will try to take this basic algorithm and try to close the gap to what MKL is doing, right? So we will do a lot of optimization so that we can get better performance. So that's what we plan to do today. So before we go to that, let me just address the feedback question that we got from last time. So one of the question was, can you explain all the scripts that we are using, right? So let me quickly go over to a command terminal here. Hopefully you're able to see this. Let me know if you want me to make the size a little bigger. So I go into the folder, and then usually the way we compile any DPC++ code is we use the compiler dpcpp, and then we go into the directory and select the file, right? So in this case, we are using the basic kernel, and we have a single source version of this one. So all you do is like just dpcpp and then the actual C file name, right? So this will compile, and then if you want to run this, it would have created an output file, and then you do a.out, and this will actually execute that code, right? So if you you might have noticed last month we explained that we have actually split the code into a common code as well as the actual kernel code. So if you're having two C++ files, so then we'll include that. This is the common code, and then the actual kernel will be basic. So you just same way dpcpp, and then we have the two source files. Same thing. This will compile in a second or two, and then we'll generate the output binary, and we can execute this one, right? So so one of the scripts we are using is mainly to do these two steps, right? Compile and run. So that's what we are doing when we actually use the run script. So you can see that this is exactly what we are doing, just two commands. We are also doing environment variable initialization. So this is not really necessary on the dev cloud, because by default it does set this when a terminal window is started. But if you do install the toolkits on your local system, you might have to do this as your first step. And then we have some arguments here that are being passed into the compile and run scripts. You can see that the compile is done similarly to what I showed in the command line. So mainly we do dpcpp and then the two C files. And in this case, we are actually giving a name for the actual binary to be generated. And then we just run the actual binary. So that's what the run script is doing. So if you want to try the run script instead of manually typing in the compile script, so you can also do run basic. So this will do the same thing, which will compile first, and then it will run, right? So this is one of the script we are using. The other script you might have noticed in the Jupyter notebooks itself is that when we actually run it in the Jupyter notebook, instead of just running the run basic.sh, we are also including what's called a queue, right? So queue is a script that we have written. It's mainly a wrapper script. So instead of running it as a run basic, what we do is we just do a run the queue script and then pass in the actual run script to this. So let's try to understand what this queue script does, right? So by default, when we run, you can notice that it's actually running on the local node that we are logged into. So if you look at what this local node has, I'll do a CL info -L, and this will actually list out all the devices we have on the system. You can see that this only has a CPU available. This does not have a GPU. So what if you want to run this script on a GPU system, right? So the way we do it on DevCloud is we submit the job using qsub commands. So you can, so that's what this queue script is actually doing. Instead of running just the run script, if you actually run it as run basic.sh, so this will actually go and find a Gen 9 node on the cluster, DevCloud cluster, and then we'll submit this job on that particular node and get back the results. So the way it works is, so let's look at this actual queue script. So you can see that it looks pretty big, about 70 lines of code, but the actual thing, one command it's actually running is this one right here, right? So it's doing a qsub, and then it's submitting to a node, whatever node we have picked. By default, it picks Gen 9, and then the script, right? So when we do this, it submits and then exits out of it, right? So then it's it will take a while before the code is actually run on a Gen 9 system, and then the results are actually written to a file. .o and the .e file. .o file will have the output. .e will have any output. So what this script is actually doing is instead of submitting and then constantly checking whether the queue is complete or not, we have written a script which will submit and then will poll for the result file to be generated. So you can see that first thing we do is like submit this one, and then we sit in a loop and then wait until every 1 second we wait and check whether there is a file generated, right? So whether a .o file is generated. If there is a file generated, it will just print out that output file. So that's what this script is doing. So it gives you more of a connected experience. So instead of constantly checking whether your job is done, this will submit and wait for about 60 seconds before the job is to see whether the job is complete. If it is not complete within 60 seconds, we just time out and then we print out a message saying that it did not complete within 60 seconds. So please check for this output file later, right? Because if all the nodes are busy, you may not get the results within 60 seconds. And also it depends on how big your application size is, right? What's the runtime of your application? So that's what this queue script actually does. But mainly it's used if you are just logged into one terminal and then just trying to submit jobs to various different accelerators. If you don't want to use this queue script, you can log into interactive terminals and then just run the run script directly. So that's what we've been doing in the session last week. You can see that I have a bunch of different terminals open. So what I've done is I've logged into different hardware nodes. So let's look at what all the nodes I have logged into right now. So I have this first terminal, which only has the Xeon Gold 6128 processor. And I also have logged into an interactive node, which has a Gen 9 GPU. So you can see that here. So this particular node has a Xeon CPU, and plus it also has a Gen graphics PCs 630. And then I also have a third window which has a dual GPU system. Both have a Iris Xe Max graphics device, right? So we will be running, today's session, we will try to run all our algorithm applications on these three and then try to compare the results. So hopefully the question people had is answered with those scripts. So with that, let me go over to the second notebook that we have. So mainly today we will try to understand. Okay, before that, it looks like there's a bunch of questions. So let me try to answer that. Yes, I think somebody asked. Okay. Okay, looks like Ben is answering all the questions. So let me get started. So mainly in today's session, we will look at ND-Range implementation of matrix multiplication, right? So last week we looked at the basic implementation that was just using a basic parallel kernel. So today we will look at what is ND-Range and then how it is useful to get better performance. So mainly what ND-Range kernels enable us to do is group your entire iteration space into small groups called work groups. And then depending on the hardware you have, multiple of these groups can be executed at the same time, right? So the GPU hardware, for example, has multiple execution units, and based on that, you can these work groups get scheduled in parallel, so that way we can get better performance. So the way we define the kernel is instead of just specifying the entire range, now we can actually specify ND range by where we pass in the global size and we also pass in the work group size. And then the rest of the code will look the same. And if you want to get a visualization of how each work group matrix multiplication is done, you can see that in this case, we are, to understand easily, we are assuming the matrix size is 8 by 8, and then we have a workgroup size of 4 by 4, and each of these 4 by 4 blocks, are computed on in parallel on the hardware, right? So you can look at the actual kernel code here. You can see that again, like I showed above, instead of using just a basic parallel kernel, we are using ND-Range, and we are specifying global size and workgroup size. But the workgroup size here is can be changed using command line parameters. So that the code for the common code, as you know, let me open that one as well. In the common code, we actually have we get the command line argument with the parameter -m, which we can actually specify. If we don't specify anything, it will assume a value of 16. So you can see that it gets the so it gets the value from command line parameters, and then we use that as the work group size and to the calculation. So let's quickly run this example, right? So let me go to the terminal, which just has the CPU. So in this case, if I want to run this, I'll do run ND-Range.sh, and this should compile and run on the Xeon CPU. Right, you can see that the offload device was the Xeon CPU, and then you can see that the maximum workgroup size is printed out. So this is just doing a device query, is 8192, but then the size we are using in this case is 16 by 16, which is 256, and you can see the execution time and then the total compute duration. So if we want to do the same thing on Gen 9 graphics device, so we can do the same thing. Just do ND-Range.sh, and then this should compile and then run on the Gen 9 GPU. Right, so you can see that the offload device here was UHD graphics P360. So this is the Gen 9 device, and you can see that we get some performance numbers here, and the same thing we can do in the Iris Xe Max GPU. So again, you can see that we get different performance numbers. So if you want to try different matrix size, you can do that as well. So if you want to directly run, since the binary is generated, so you could do ND-Range. So this will run the default values. If you want to run a different matrix size, you can do that. You can do something like 5000 by 5000 matrix. So this will take obviously longer time to execute. So let's wait and see if we get an output here. Right, you can see that for 1000 by 1000, it was actual compute duration was like 0.1 second, and you can see that when we change the matrix size to 5000 by 5000, it takes about 16 seconds to do the same thing. So let's look at the actual numbers, right? So you can see that we have collected all the advisor roofline reports. So if you run this cell right here, this will give us all the roofline reports for collected on Gen 9 as well as the DG1 for different matrix sizes. So you can see that you can see how much headroom there is for improvement based on what matrix size we have and based on what hardware we are using, right? So this is these roofline reports will be useful once we have all the optimizations, and then we can start comparing how this dot actually moves up in the roofline graph, right? So something to keep an eye out for, once we start doing different optimization. And we also have collected a lot of VTune reports for all the different matrix sizes, and also the various different GPUs that we have. So you can see that in the basic summary, this will actually give you more information about uh, how much of the EU array was stalled or idle, and then what is the uh, peak occupancy value, right? So you can see that when it is 1,000 by 1,000, we have about 83%. And then when we go to a much bigger matrix size, you can see that the occupancy is like at 99% here, and then same thing, 99.8%, right? And you can also see the entire time it takes, just the GPU time versus like the actual elapsed time, right, for different matrix sizes. So when we just executed this one, we noticed it was around 16 seconds, so pretty consistent. So these are all was collected a while ago, and then so you guys can actually run the same thing. So if you do want to collect these VTune numbers, so there is a script available here called vtune.sh. So mainly what this does is it's written so that you can test all the different matrix sizes at once, or you can just specify like what matrix size you want to collect data for, specify the workgroup size, and then what device you're running and where the binaries are located, right? So in this case, you can change this to whatever binary you're testing and then just run the script. So this will has two main commands. So one is it is collecting the GPU hotspots, right? And then it generates a HTML report for VTune. And that is exactly what we are seeing. So if you want to run this one, so let's quickly try to run one of the reports. So mainly we are running this script. So if we want to run it for the ND-Range version, so let's put the binary name as ND-Range, and then I think we are doing this on Gen 9. And the rest of the values can be same. To make this quicker, let me just do something like 2048. So this is a 2000 by 2000 matrix size. So let me go on to the Gen 9 and run the VTune script. So you can see that it is collecting the GPU hotspots, which would take about few minutes or a couple minutes maybe. So let's wait. You can see that the actual binary is being run, and then you will see a detailed report being generated. So you can also see that while this VTune data is being collected, it also created this folder called vtune_data. So this has all the information it's collected, right? So right now on the dev cloud, all you can do is like use command line to run VTune. But if you do want to use the full version of VTune and analyze it, so you can always zip up this vtune_data, copy it to your local machine, and then use the local version to do all your analysis. So if not, I mean, this will at least just generate like a HTML file that you can look at and get most of the information about how well your application is doing. So let's wait. So it looks like it's about 50% complete. So let's wait a few more seconds. Okay, so there's a question on So somebody said, can you please show what parts you changed? So let me go back to the vTune script here. So all I did was change the matrix size to whatever value. You can also specify multiple different matrix sizes, like the commented code here. So what it'll do, it will first capture the first one and then go through a for loop and then do the second one, right? And then the device is Gen 9, so I just this is just for creating the HTML file, and then the binary name. We can either list one or many here. So that those are the things that I changed. And then let's go back to the command line. So it looks like it's complete. And then you can see that at the end of this report, it actually prints out all the summary in like basic text form in the command line. But if you look at your home directory, you can see that there's a new file generated, which says vTune and the binary name, and then which hardware it was run on. So if I double click on this one, so this will open up your vTune summary report. So you can see that the elapsed time was about 4 seconds, and then 1 second was spent on the GPU. And it shows you, other numbers like how much, 2.5% of elapsed time, 56% of the peak values, the L3 bandwidth. It gives you basic summary and also like the hardware details, right? So you can see that this analysis was done on the HD graphics P630, and then you can also see the type of hardware it is. You can see that this particular Gen 9 GPU has 24 EUs on it, right? Okay, so that's how you generate the vTune report. So now that we have the ND-Range implementation, so next look at how we can actually improve this one. So let's look at the code that we wrote here, right? So you can see that the actual computation is being done right here. So you can see that it goes through this for loop 0 through n, where the value of n is actually the matrix size, so 1,000 or 2,000, whatever, right? So 1,000 times it's actually overwriting this particular value, which is the matrix output matrix C. So when C is accessed directly, it's actually writing directly to global memory 1,000 times. So if we increase the matrix size, we are actually writing to the global memory, in a much larger number. So there is one optimization, very basic optimization we can do is like we can actually, instead of writing, since this is updating, we don't have to write directly to global memory. We can first write it to a private memory or register, right? So if we just create a variable, a temp variable, and then outside the loop, we can actually update this once to the global memory, right? So that's the basic optimization we're going to do next. So that's what I'm talking about, is mainly instead of constantly updating the global memory, what we will do is we will create this float temp, right? Initialize it for value 0, and then we keep on updating this temp value, and then once this is done, we actually update the global value, right? So what this will do is if we create a float temp, so this is actually using the private memory, or it's just a register in the hardware, so the latency is much lower. So and that's what we are doing here. You can see that it's same as the previous code example. So the second example, mainly we are calling this ND-Range with using private memory. You can see that we declare temp, and then we use actually write it to the global memory. So let's run this example and then see what kind of performance we are getting, right? So the file name of this one is ND-Range _var. So if we want to compile this one, we can just do run ND-Range var.sh, and then let's compile and then get some results. At the same time, meantime, I'll also run the same on the Gen 9 node here. So you can see that this was executed, and then we got some numbers here. You can see that the previous result, you can quickly compare that, and you can see that the second implementation is slightly faster, right? Same thing here. You can see that we have some output, and if you keep on trying this for different matrix sizes and plot all the results, you should actually see a slight improvement in performance, right? So again, here we have the roofline report as well as VTune profiler summary. So we can quickly look at that one as well. Same thing with the roofline. Right, so here you can actually compare, for example, the Gen 9 1000 by 1000 matrix along with the Gen 9 result we are getting here. You can see that where the actual red dot is at, right? So this will actually show, how much, bandwidth is actually using compared to the other one. So you can see once you hover over this red dot, you can see that the effective bandwidth is 1.6. And you can compare that with the second implementation we have here, right? Right, so we have like different values here, total flops per byte. So we have collected all this information for you to, analyze and see what are the differences between the two implementations. So and then also the values, right? So for different matrix sizes and also different GPUs that we have used to collect the same information. So if you actually plot the graph, you can see that the one in orange, which is the one that's using private memory, you can see that it's slightly better than the previous implementation, right? So you can see that not by much, but maybe 10% or so better performance. And you can see that when you, depending on the type of hardware you're using, you can see different numbers. So the main difference between Gen 9 and the Iris Xe Max GPU that we are using is that the Iris Xe Max is actually a discrete graphics, whereas Gen 9 is integrated graphics. So that's why we see that the performance gains while accessing global memory is kind of more significant when you're using discrete graphics, because the memory is on a is a separate memory, not the system memory. So that's why using less global memory actually has a better impact when using discrete graphics here. So let me know if you have any questions. I can run a few more examples here for using different matrix size. So if you quickly want to compare values, so we can do, let's say, matrix size 5120. This is I'm on the Gen 9 hardware here. Right, and then we can do the same thing with a different implementation without using the private memory, and then see what kind of results we get. Oh wait, I think it's still using 1000 by 1000. So you can see that when we are using the ND-Range var, you can see that it's slightly faster, right? So it's 0.24. So if we want to change the matrix size, so let me actually call the binary 20, right? So now it's actually using matrix size of 5,000 by 5,000, and this is without using private memory. So let's get some numbers here. Right, so about 13.5 seconds. So now let's run the same thing using the private memory version. Yeah, as you can see that it's about 12 seconds here. And then if we don't use the private memory, it's about like 13 seconds, right? So as and when the matrix size becomes larger and larger, you will see like a significant improvement in performance. So let me know if you have any questions in these two implementations so far. So mainly what we are trying to do here is, from last month's basic implementation, we are trying to build on top of it and doing small optimizations and then uh, trying to collect all the numbers at every optimization, right? So at the end of it, we will have a bunch of optimizations and then we will see how, each of those implementation actually impacts the overall performance portability. So if there are no questions on this topic, then we can move on to one more implementation. So far we looked at just using ND-Range and also looking at using just a private memory memory. So the next one we will look at using local memory, which is if you look at the actual graphics hardware. So let me pull up a picture. Right, you can see that a GPU, we have a bunch of these sub-slices, right? So this is using Gen 11 graphics as an example. So you can see that each of these sub-slices where your workgroup is actually executed, right? And then you can see that each of these have what's called SLM, which is mainly shared local memory, which is available uh, for these execution while the execution units are executing. So the size of this is typically about 64 kilobytes in case of these graphics hardware, and on the CPU it could be different. I think it's like 32K, right? So this memory has less latency than accessing the global memory. So that's what we will be looking at the the fifth implementation mainly. So we will look at how it works. So you can see that when we have a bunch of work groups, so all the work groups can actually access the global memory. The latency is much larger there accessing, but then each of the work group also has access to its own local memory, right? So this is a smaller memory, about 64 kilobytes, like I said, for graphics. And this is something that can be made use of to get like significant performance. Right. So to use that, let's look at our kernel implementation of matrix multiplication. So you can see that in this case, what we are doing is, again, we have the accessors for matrix A, B, and then C is the output matrix. And similar to the previous implementation, we have the global size and the workgroup size defined here. And then you can see that we are creating two local accessors. So this is where we are creating mainly like two tiles for matrix A and B, which is, and we define the access target as local. So mainly that is where defining that this is where this is using local memory, and the size of local memory is same as the workgroup size, which is M times M. and the type is also defined here. So this is actually creating two local memory uh, objects here. And the reason we are doing this is that if you look at the, let me go back to the picture with the matrix multiplication, right? So the way matrix multiplication works is that each row here is now multiplied by a column, right? So you can see that to get the value of this work item here, what we do is like multiply this row by this column, and the same row is multiplied with the second column and third and fourth and so on, right? So you can see that each row is multiplied by all the 8 columns here, and then we have to move on to the second column, and then this second column again multiplies with 8 columns here. So what is really happening is that for each of these 8 operations, it is actually copying the same matrix 8 times. So the idea about using local memory is that we first copy the entire matrix into local memory, right? And then the subsequent 7 times, instead of getting it from global memory, you're just copying from local memory. So that's what this implementation actually does. So you can see that the matrix multiplication we are doing, slightly changes. So instead of we we get the tile, we load the tile, which is the local memory, is the target. We copy from global memory into local memory, and this local memory is what is being used for our calculations, right? So you can see that instead of accessing global memory right here, in the for loop, we are actually just loading the local memory once, and then within the loop, we are just using the local memory. So that will actually reduce a lot of global memory access, and since the local memory access has less latency, you should be getting better performance. And we are also using these barriers here, right? So mainly it is making sure that all the work groups are synchronized first before the actual computation is done. So if there are multiple work groups executed, so this barrier will make sure that it will synchronize all the different work groups so that all the local memory contents are loaded. And then that's when the actual computation is done. And again, we do another synchronization. And then finally, again, here, what we are doing is we have created a private memory, a temp variable, and then finally updating the actual result in global memory. So with this implementation, let's execute this on the various hardware we have. So the first thing, so this, let's check what system this is. So this is a system with just a CPU. So let me go ahead and then run the local memory version. So this should compile and then execute and give us some numbers. So here you can see that this was run on the Xeon Gold, and the matrix size was 1024 by 1024. So we can also run another size. So let's access the binary directly. So you can see that it took 0.1 seconds here, about 3.6 seconds for 5,000 by 5,000. And let's also try 10,000, right? So while this is executing, let me switch to the terminal with Gen 9. So again, so this system has a Gen 9 graphics device. So let's do the same thing. So we can do just default with 1000 by 1000, and then let's also run size 5120. Took about 9 seconds. We can also try 10,000. So here you can, right here, when we did the previous example, you can see that ND-Range example took about 13 seconds. The ND-Range with private memory took about 12 seconds, and then straight away you can see that when we're using local memory, we are seeing significant performance gain here. Again, it takes about 9 seconds. So let's see. So looks like this computation on CPU for size 10,000 is also complete. Took about 33 seconds here. So we can do the same thing on the Iris Xe Max device. So let's do CL info quickly here. So this is a system with Iris Xe graphics. So again, here we can run just 10,000 by 10,000, 1,000 by 1,000, and then the second one is 5,000 size. Takes about 11 seconds, and then we can also run the 10,000 matrix size. So let me go back to the Gen 9 terminal, and you can see that the 10,000 by 10,000 was complete. Took about 72 seconds here, right? So you can try all these different values on all this different hardware we have on the dev cloud, and then we've actually compiled all the reports here. Again, you can see the roofline reports. Yeah, again, you can see that the between mainly in the effective bandwidth, you can see that it's about 2.08 gigabytes per second, and you can do a quick comparison with without using local memory, right? So if we go here, Gen 9, and you can see that it's 1.6 here on memory traffic, and then you can do a quick comparison here, right? So same with various vTune profiler results, right? So for 10,000 on 5,000, as well as 10,000 again here, right? So it's kind of consistent with what we saw here, right? So it was about 72 seconds, 9 seconds, and then 0.2 seconds, and that's what we are actually seeing, about 74, 9 seconds here, and then about 0.1 seconds, right? So if you do want to run the same the roofline analysis, so there is also a script for that. So if you go into the main directory, we have a script called the roofline.all, right? So again, it's about the same way that we did for the vtune script. You can go in and then change these values. So it looks like right now it's set up to collect information for matrix size of 5,000, workgroup size of 16, and then we have we're collecting on Gen 9, and then we are using the local memory binary, right? So the script is ready as it is, so we can go on a Gen 9 node and run the roofline report. So again, this should take a couple minutes or so. So let's wait and see what we get. So let me go through the questions in the meantime. So the question here is, would the private memory be L3 on the shown graphics? So it's not L3, it's mainly, if you create a variable, it's just like a register. It's just temporarily stored like a scratch register. Local memory is what is 64 kilobytes of memory that's available. So another. Okay, somebody's saying they don't see the vtune underscore data directory. So this is only generated once you run the vtune underscore all.sh, right? So when you run that, that's when this vtune underscore data will be created, and then you can zip that up, copy it to your local computer, and then use that to analyze if you have vtune installed. Okay, looks like this report is still being generated. So you can see that when we run the roofline dot underscore all script, it should actually generate this roofline underscore data, right? This is where all the data is being collected. And then again, same thing, if you have the Intel Advisor installed on your local system, so you can copy this folder and then analyze the results. Ben, are there any questions that needs to be answered in the meantime while we wait for this report?
It's actually a good feedback that you actually write. Yeah. Is there a cleanup script that would be all through all of this? One of the things you can do here.
Okay, I think you're kind of faint. Cannot hear you well, Ben. But yeah, I did look at the question about the cleanup script. Well, I don't think we have a cleanup script. Yeah,
I think we did. We should write one.
Yeah.
Good feedback. We'll take that.
Yeah. So the one way you can do is like, I know there's a lot of data being generated. If you do want the, the fresh copy done whenever you run this script that we ran, I don't know where it is, which is just /data oneAPI underscore workshop, and then get Jupyter notebooks. If you run the script, this will actually copy a fresh copy. So one way you can do is like just delete this entire DPCPP performance portability folder, and then run this script, which will actually copy a fresh copy of everything, right? So whenever we do any analysis report generation, so you can see that looks like the roofline report was complete. You can see that it's complete, and then all that roofline data will be in this folder, roofline underscore data, and then it's created a HTML file here. So if you double click on this one, this should give you, I'll just click on trust HTML. So this will give you the roofline report. And here you can actually go in and then check all these L3 and SLM, and then you will be able to see how much SLM is being used. You can see that the SLM memory traffic and then the effective bandwidth is also right here, right? So if you look at the same thing for the ND-Range version, you will see that you won't have any SLM because we did not use SLM in this case. So you will just have, there's no another dot for SLM. Right, so once you do the analysis and here we've actually collected all the information for both Gen 9 and then the Iris Xe Max GPU. And you can see that when you use local memory, you can see that you will get kind of a significant performance improvement, especially for the larger matrix sizes. You do see that for 1,000 by 1,000 matrix, it's not really giving you better performance. Actually, the performance is worse, right? So that kind of concludes that using SLM, it really depends on the kind of application and then how much reputed access you have, right? So just using local memory does make the code a little bit complex, like you can see, right? So if you compare this with the ND-Range version, you can see that the ND-Range one is like pretty simple, right? So it's just one for loop and then we do the actual calculation. But here we do have this extra step where we are loading the contents of the matrix into local memory first, and then we are using local memory to multiply. So there is a little bit of overhead, but then if you have larger matrix size, you will see a significant improvement. So that's what we are actually seeing here. Right, so that is pretty much what I had in mind for today's session, right? So far what we have done is we mainly in last month's session we had a basic algorithm created, and then today's session we mainly looked at 3 different versions of optimization, right? So one using just work groups using ND-Range kernel, and then we looked at an example which uses a private memory to avoid repeated global memory writes. And then we also looked at the version where we use the shared local memory, where we copy, where we load the matrix into local memory so that it's not accessing repeatedly while doing the actual calculation, right? So based on that, we have collected all the numbers, and then we are trying to analyze what are the differences, right? So that's all I add for today. So what we will do in the next month's session is mainly we will try to analyze everything and then look at how we can improve the performance portability, right? So let's quick peek into what we will be looking at. So I just wanted to show this final chart, right? Based on all the different optimizations we have. So we started with ND-Range, then we have the ND-Range with private memory, and then we have local memory, and then the MKL, right? So we can see that with every optimization we did, we do see like slight improvements, right? I mean, still using the library, we can see that it's still the best approach for now, right? But one thing we noted is that in all these implementation that we saw, we are using the workgroup size of 16 by 16 because that is like one size that actually works on all the hardware, right? So in the next month session, so we will mainly look at how we can further improve these 3 optimizations so that we can get closer to what the MKL version is giving us, right? So that will be in the next month session. But in the meantime, let me know if you have any questions on today's session, or if you are having any um, issues or seeing any weird results that needs to be looked at.